Welcome to Group B28's Through Walls Radar Simulation Report, where we will be going over the results of our MATLAB and OpenEMS experiment. In order to create and simulate a through-the-walls radar situation, we had to first create an environment in which it would be modeled. This environment consisted of an antenna and a concrete wall with an object placed directly behind it. This object could be, for example, a human being. The radar system was put directly on the wall because that's how most handheld through-the-wall radar systems actually work, as few can actually operate when not touching the wall. Our object was placed at a distance that wasn't too far as that there would be a small difference in the S parameters because little signal would bounce back. After some research, we came to decide on the parameters that we would assign both our wall and our object, so that they would be similar to that of real life. We chose the concrete wall to have an epsilon naught value of 4.5 and a density of 2300 kg per meters cubed, whereas our object was given an epsilon naught of 50 and a density of 1010 kg per meter cubed. Our antenna, in this picture the small purple structure, is the actual radar device that transmits and receives the signals with values chosen by us in order to try and approximate something realistic. The size of the simulation was large enough to allow energy within the system to not be constricted and to operate naturally. CSXCAD was used to simulate the geometries and properties which allowed us to create a physical region. A 1D port with a 50 ohm feeding resistance and a current and voltage probe was added to measure the S parameters. In order to actually measure the results, the environment was divided into many small Yee cells. Gaussian excitation was used because of the range of frequencies needed as well as a time domain measurement because of the large range of frequencies required. CSXCAD creates a physical region over which the simulation is performed. This is the computational domain for FDTD, which the antenna is our source. The FDTD uses finite difference methods / difference equations to solve for the electric field, and a dump was added to store the measurements. For our radar itself, we used an ultra-wide bandwidth, so frequencies of 2 GHz to 10 GHz were used for the antenna. These signals were passed through the wall in order to detect an object behind it. These signals were then reflected back to the antenna from the wall and from the object if it was present in the simulation. S parameters were measured because they describe an input-output relationship between the terminals. Specifically, S subscript 11 was measured, which represents the amount of power reflected from the antenna. We measured S subscript 11 in 3 different scenarios: an empty environment, the concrete wall alone, and the concrete wall plus the object. For the empty environment, the S parameter measured from the simulation was 0, as expected, as there was nothing present to actually reflect the signals. For the concrete wall alone, we found that with increasing frequency, our S parameter values are decreasing because more energy is lost as the frequency increases. This range of S parameters goes from about 0 decibels to about minus 3.5 decibels on the logarithmic scale. When the object was also added into the environment, we found that once again the S parameters were decreasing. This time, though, they only decreased from 0 decibels to about minus 1 decibels on the logarithmic scale. This shows us that our radar simulation was able to show that it did find something on the other side of the wall. The formula for the S parameter is as follows: S subscript 11 equals log of the reflected value divided by the transmitted value. When there is an object behind the wall, there should be more reflected signals than just the wall, and the transmission we keep constant, which allows us to differentiate between the two signals. As the wall alone simulation decreases to a more negative number, it stands to show that it has a smaller reflection-transmission ratio, meaning there is less reflection. The ratio will realistically always be less than 1, so the S parameter will always be less than 0. The more reflection with the object means a larger ratio, and therefore a less negative number. At first, we did not run our simulation long enough. We weren't using enough time steps for a simulation as large as the one we were running, so we were getting random outputs. To fix this, we set an end criteria to run until there was very little energy left. This allowed the simulation to have a long enough runtime to properly simulate our environment. Some obstacles that we ran into along the way were little documentation on OpenEMS software beyond a rudimentary level, and lots of experimenting with different methods was needed in order to obtain our final results.